All right. Hi, everyone. Welcome to another online causal inference seminar. Today we have a treat. We have many people joining us here as speakers, discussants, panelists. So I hope you'll all join me in welcoming Matias Cattaneo from Princeton, who's going to give a talk on estimation and inference in boundary discontinuity designs. Apologies. And we have two discussants today, Alberto Abadie from MIT and Kosuke Imai from Harvard. We'll be doing a discussion one after another after Matias is done with his presentation. Actually, Sarah is handling the questions, so I'll switch over to Sarah.
Okay, I'm just here to remind you to please use the Q&A part of Zoom, and instead of using the chat for your questions. And then there is a co-author of Matias, so there's Re, who will answer some of your questions, and she will flag which ones we should discuss with Matias either in the middle or at the end after the discussion. So this is all from our side. So without further ado, I would let Matias start his talk. First share the screen and then start his talk. Yes.
Okay, great. Thank you so much. And thank you for the opportunity to present the work here. So let me try to share this. Okay, there we go. Okay, let me try to reduce distractions in different places on my screen. I think I can do that. Okay, excellent. Okay, so I think I'll get started. I aim for a 40-minute talk. That means that I will only be able to talk about a couple of things that the paper tries to do. But incidentally, I think there is really one idea or one result that, I mean, at least for me, coming into this project was a little bit unexpected. And in some sense, I think perhaps justifies the existence of the overall work. Okay, so let me get started. So as it was already announced, the title is Estimation and Inference in Boundary Discontinuity Designs. And so I'll give a self-contained presentation trying to introduce the idea of boundary discontinuity designs if you haven't seen them before. And this is joint work with Rosiotti Tunic at Princeton University and Ray Yu as well as Princeton University, who is actually handling the chat. So all the questions, hopefully she'll be able to answer. Okay, so this is kind of a walkthrough of the presentation. I won't have time to talk about everything in here. As the titles already suggest, there are a couple of ways that you can proceed to conduct estimation and inference in this setup, one of which we label as distance-based methods and the other one location-based methods. And this dichotomy is going to play an important role. So each of these methodologies are going to have pros and cons. And in particular, we're going to highlight a potentially worrisome feature or pitfall, I would say, of the distance-based methods. And it's kind of interesting because this methodology is relatively widely used in applied work in causal inference, relying on boundary discontinuity designs. And so there are some concerns and potential drawbacks that this methodology might have. And then I'll try to illustrate a little bit of the methodology with an empirical application. And I added a couple of slides on aggregation along the boundary. This is not technically part of the paper. We're writing a follow-up paper for the World Congress in the Econometric Society. But this is a question that comes often when I present this paper, time and again. I mean, as you will see in a minute, practitioners often approach this in different ways. And one of the ways is by just running a simple regression, aggregated kind of regression analysis along the boundary. And an obvious question is how these things are connected. And there are a couple of slides at the end that if we get there or otherwise in the Q&A, we can kind of go through. Okay, so let me get started so we don't lose a lot of time. So boundary discontinuity designs are arguably widely used in causal inference and policy evaluation. They are a natural generalization of traditional regression discontinuity designs. Sometimes they are called multi-score or geographic RD. This is a very common application that you will find in many different disciplines. There are two, I would say probably three really ways of doing this. The original way was one where you will grab the boundary will separate or split units into groups, and then you will localize to the boundary in some way. And once you were there, you will just run literally a difference in means or maybe a regression type of adjustment, comparing units in each side of the boundary, and you will just report a single estimate. And so that was kind of the original approach. It goes back all the way to maybe David Carr and Alan Kruger with a minimum wage paper that compared the boundary between New Jersey and Pennsylvania. And then from there, a bunch of other well-known papers by Melissa Dell and Caroline Hosby and many other people that have exploited these changes in assignment of treatment along a certain geographic or otherwise boundary discontinuity. More recently, I think people realize that it makes sense to extract some heterogeneity along the boundary. And so instead of doing a single pooling type analysis of all the units on either side of the boundary, people realize that maybe it's better to localize along the boundary. And so more localization has emerged, I think, in empirical work. And with localization, different approaches also emerge as well. So here I highlight the two more common ones. So one is the what we're going to call here distance-based. And the idea basically is that you will localize along the boundary, and for each point on this grid along the boundary, you will compute distance to that point for each unit. And then you will proceed as if this was a one-dimensional regression discontinuity problem, because you will just essentially metrize the distance of each unit to each point on the boundary by a one-dimensional metric. That's fine. So that's what we're going to call the distance base. And this is quite popular in applied work. So there are quite a few papers that do this, partially because we are at fault here. We recommended them to do this. So I guess part of this paper is correcting ourselves. So after we recommended this in a bunch of places, we kind of realized that, I mean, there is a sense in which this methodology may not be the best way to analyze this boundary discontinuity designs. And so the alternative to that is the so-called bivariate location. And this is kind of a straightforward, so I won't really talk much about this. It literally says use just the bivariate location space and then analyze this as a bivariate non-parametric problem. And so that is super straightforward. So I'm not really going to discuss almost anything on this. Is in the paper mostly for completeness. I think what makes the paper arguably interesting is the fact that the univariate distance-based methodology might not work the way that we typically expect it to do. Okay, great. So then, as I said, I'll talk a little bit about aggregation as well. And so here is a little bit of a summary of what the paper tries to do. And for those who are interested in more applications, we have an R package that we're about to release a new version now with some upgrades, including some results on aggregation. And you can actually check it out on this website. Okay, so let me try to get motivated a little bit why we're doing this. So here is a very prototypical application these days. Many papers have studied this, including ourselves in some monographs before. This is a data set from Colombia. It's a conditional cash transfer type program. It's an anti-poverty program. It's called Serpilo Paga, SPP for short. And each unit here is a student graduating from high school, and students may or may not receive, or at least be assigned to receiving a subsidy to go to college, a certain cash transfer, depending on two things. The first thing is that the students should perform sufficiently well in an exit high school general exam, and that exam is called the Saber 11. So units along this dimension are units that perform either poorly, mediocre, or really well in the exit exam. So as you move in this direction, units are performing better. They're doing better in the exit exam. Then also, they were supposed to be not too wealthy, right? So in order to receive or be eligible to receive this transfer, students should not be too wealthy. So again, students along this direction are wealthy, not so wealthy, poor, right? So as you move down here, you find students that are relatively poorer. And so the idea behind this assignment was that students should perform sufficiently well and also be sufficiently poor to be eligible. So all the students that are in this region here, which I'm going to call A1, those are students that were assigned, they had wealth and exit exam such that they belong to the assignment to treatment region. And then all the students that are on this region here, they are students that were assigned to group 0, A0. And so as you can see, this is nothing more than a generalization of a regression discontinuity design. And naturally, you would ask questions such as, well, the causal effects of receiving this transfer might be different for students in this region of the boundary vis-a-vis to students on that region of the boundary, right? So as you move yourself down this boundary, students are getting richer to the point that then become ineligible. And then students that move along this way in the boundary, the students are getting better at taking their exam and potentially capturing some underlying trait. Okay, so basically, if you can, in principle, analyze all the data that is around the boundary, and that was the original type of approach that people would do in the past, and that will become essentially an aggregation and single treatment effect estimate for everybody, disregarding heterogeneity along the boundary. More recently, I think people realize that it's better to discretize and do a little bit more detailed analysis along the boundary. And so in this example, we have 40 discretized points that capture different evaluations of a continuous function that lives on top of the boundary. And this function we're going to call the causal treatment effect curve, right? And so this will be nothing more than the usual Abadie type average treatment effect at the cutoff. But now the cutoff are relative to each of these grid points that discretize the boundary. And so, as I always do in my talks, whenever something is going to bring trouble or potentially requires attention, I'm going to put them in red. And whenever I see something that is good and we like it, we're going to put it in blue. And that in no way captures any of my political views, but nonetheless, red is going to be typically bad and blue is going to be typically good. And in this case, as you can see, I put in red the kink point. And so this kink point is going to bring some interesting features to bear and potentially is going to highlight some issues with one of these approaches that I mentioned before. Interestingly enough, it will not happen at the kink, but it will happen rather near the kink on each side of the kink along the boundary, as you will see in a little bit. Okay, so just to summarize a little bit how local regression analysis based on distance goes. As I mentioned before, each value here corresponds to a score value containing, in this example, the exit exam score, as well as the wealth poverty index, a bivariate score, but then it's reduced to a univariate metric where this D symbolizes a distance. So for the purpose of today's talk, I think it's very easy to just think of this simply as Euclidean distance, right? For simplicity. So the L2 distance, that's perfectly fine. And most of what I'm going to say today generalizes to other distances, but Euclidean seems to be the most natural thing to think about. Okay, so in order to kind of explain how things work and then show you what's good and bad about this, we put together a little bit of a simulation study first. So what we did is we grabbed this data, which is real data, and then we decided to calibrate a simulation experiment by first choosing the underlying features of the data generating process. And in particular, what we did here is we literally ran a linear regression on the control group, meaning all the units here, and then separately, all the units here, and then on the treatment group, which are all the units there. And so we chose a linear model, not because we believe the underlying conditional expectations are linear, but just because that would allow us to remove all the smoothing bias that you might encounter if you were to parameterize these conditional expectations in a more, in a richer way. And so once we settle on this particular DGP, which you might like it or not, it doesn't really matter, it's just for illustration at this point, then what we did is we started to simulate data, and then we tried to compare the performance of the two main approaches that I mentioned before. So the first approach is the distance-based approach. So the idea is that you position yourself at each point of the grid. We're going to start with B1, and we're going to walk our way out down the boundary. So for the very first point, we're going to compute the distance of each unit, let's say Euclidean distance to that point, and then we're going to reduce the bivariate score to the univariate distance score, and then we're going to just run RD in one dimension. So this is straightforward. This is what we recommended before, for better or worse, because once you are in the one-dimensional world, you can just literally deploy everything that you think you know, and certainly all the software that is out there for univariate RD designs. And so if you repeat this experiment 1,000 times and you take the average of that, you will see that the average estimate for B1 of this average treatment effect at the boundary happens to land there, and it's a little bit away from what it would be the population treatment effect curve, right? So of course there is this little distance there, but we don't really know what's going on. We're just showing you one point on the grid, okay? And so the rest here is purely notation, which hopefully you are a little bit familiar with. This is just a convoluted way of saying that we run a local polynomial, often local linear with p equal to 1, local linear regression on either side of the boundary as determined for this cutoff B1. Okay, so then we can also do the blue approach, let me call it, which is just this local polynomial based on the bivariate score itself. So this is a bivariate non-parametric regression. This is very straightforward. And in this case, of course, there is no smoothing bias. So by construction, you better get it right on average, or otherwise something more fundamental would be happening here. And indeed, you can see that the blue average of 1,000 realizations of this average treatment effect for the point B1 on the boundary happens to lie right on top on the population condition expectation capture or difference thereof, which capture this treatment effect curve along the boundary. And so then we can continue on. And so this is what would happen if we did the first 10 grid points along the boundary. And as you can see, of course, the bivariate fit or the bivariate approach works really, really well, the location-based approach. And the distance-based kind of starts doing better as you approach more of the middle of this segment of the boundary. Of course, this is just one example, right? We need to write some theory to understand what's going on. But nonetheless, the simulation suggests that as you move away from the boundary of the support of this bivariate score and you go towards the middle and you have a nice line on the boundary, assignment boundary, then things start to work slightly better. And then as you move further closer to the kink, so now we are at the point B15, which is right here, then you start to see that all of a sudden the distance-based, the univariate distance-based approach tends to exhibit, again, kind of a larger bias. And then if you continue on, then you see that when you hit the 21 point, the point 21, which happens to coincide with a kink point in this case, you exhibit some bias, but then all of a sudden the bias sort of goes away. And then you continue on, and then you see again that there is this large bias that happens near the kink, incidentally not at the kink, near the kink. But then as you move farther away from the kink, this bias tends to disappear again. And so kind of the main point that we're going to try to make in this paper, and this is kind of the result I mentioned was a little bit unexpected to me at least, coming into this project, is the fact that we can formally show that this distance-based approach in general will exhibit a large bias near kink points, or more generally, near points on the one-dimensional assignment boundary that are rough in a smoothness sense, as you will see in a little bit. So kinks being an obvious example of that. And so the main implication, practically speaking, of course, is that distance-based methods might have biases that are substantially larger than their location-based or bivariate-based counterparts. And so if you are worried about this potential bias as misleading, giving you misleading conclusions, then possibly you would prefer not to use distance-based methods and instead use the location-based methods. In some applications, you cannot really escape it. I mean, I should mention, and this is something I got some pushback when I've been presenting this paper, you cannot completely dismiss the distance-based methods, sometimes for confidentiality reasons or assignment mechanism reasons. Sometimes all the information that you have are distance and is not really the location itself. And so in those cases, this paper really brings to bear issues with the distance space that you would have to pay extra attention to in order to make sure that the results are, well, robust or credible. Excellent. So the paper also discusses inference along the boundary. As I said, this part is not particularly surprising. I think it requires some dotting I's and crossing T's, but ultimately we have now a set of tools that allow us to do this fairly straightforwardly. Here I'm plotting pointwise confidence intervals along the 40 grid points. Of course, we understand that if we're trying to estimate a function along the assignment boundary, what you really would like to have is some notion of uniformity along the boundary. So the most natural thing here is to construct a confidence band. And so we also do that in the paper. It requires a little bit more work, as you might imagine, because now you have to account for the joint inference problem along the boundary, the assignment boundary. But in itself, I would say that is not particularly hard at this point. We kind of have the tools for it. Again, what I think is kind of surprising is the fact that you can really have these substantial biases near the kink points whenever you use distance-based methodology. Okay, so I hope I was able to motivate a little bit why this paper exists and what kind of problems you might face with these distance-based methods. So the next 20 minutes, I'm going to try to explain why this phenomena happens and where is this coming from and to what extent this is unavoidable, or perhaps how you could try to fix it if you could, or otherwise what you should be looking for to make sure that this problem is not too pronounced in your application. Okay, and then I'll try to show a little bit of the results empirically. So here is the roadmap for what we're going to do today. So I'm going to focus a little bit on identification results based on univariate distance. That is fairly straightforward, so I don't think it's going to be difficult to get there. And then I'm going to spend quite a bit of time trying to explain what this large misspecification bias for non-smooth boundaries is about, okay? And so just to reemphasize, in the previous simulation that I showed you, there was essentially, in principle, one of the simplest possible data generating processes, right? So the underlying condition expectation was actually linear to begin with. And so when you reduce the problem to distance-based, all of a sudden you generate these biases, potential biases near non-smooth regions of the assignment boundary, even though the underlying data generating process is substantially easy or simple in some sense. And as, I mean, if depending on where you come from, you might or might not expect this result, but nonetheless, you can hopefully guess that because of the simulations I show you, there were regions where things were working well, in particular, those regions where the linear segments of the assignment boundary away from the kinks. And so that idea can be generalized within our theory. And of course, if you have boundaries, assignment boundaries that are smooth in some specific sense, then that smoothness would translate into a better behavior or lack of misspecification biases for the distance-based approach. And so this is kind of part of the recommendation as well. So if you think that you have boundaries that are smooth enough, then this type of problems would not appear. But if you have boundaries that are a little bit more non-smooth, like for example, in geographic settings, you will have boundaries that look like that, right? So this type of boundaries, for example, here might have quite a bit of these potentially kinks. And so in those cases, conducting distance-based inference along this boundary might bring some of the problems that I'm highlighting today. Okay, perfect. So after that, I think the rest is going to be fairly straightforward. I mean, so I won't spend a lot of time on much of that afterwards. Okay, so here is the main setup for the distance-based methodology for causal inference in boundary discontinuity designs. So as I said before, the parameter of interest is the average treatment effect along the boundary. Is a curve, so we're interested in that. The way that we're going to do it is basically we're going to run two regressions, one regression from the treatment group side, one regression from the control group side, very much like in traditional regression discontinuity designs. And the way that we do that is by reducing the bivariate location to a univariate distance metric to each point along the boundary. Okay, and so this is a little bit of notation here, but it's fairly straightforward to unpack. So we're running local polynomial regressions. P is often 1 for local linear. There is a kernel smoothing, which is scalar. It takes the distance to each individual point along the boundary. In practice, you discretize it. The more discretization, the better. But of course, you generate more local correlations as well that would need to be taken into account. Then the bandwidth is the key parameter telling you how much localization you do for every 1 point along the boundary. And this indicator here is just our way of keeping track of whether you are coming from the treatment side or the control side, right? As distance goes to 0, you are effectively approaching the point in the boundary, on the boundary that you care about. Okay, so we have a bunch of regularity conditions for the data generating process in the paper, but those are fairly standard. None of those are going to be driving the result I'll explain today. In fact, you can think of this underlying treatment effect curve as being very smooth, very nice. I mean, analytic, if you like. So that's not going to be driving the result today. As for the kernel, again, there's nothing suspicious, or there are no dead bodies here. I can tell you what the dead bodies are later, but certainly not here. So the kernel is fairly standard. It's either compact supported and libgits, or otherwise maybe the uniform kernel, which is something that people use often in practice. This additional condition here is new, I guess, to the literature. I think a couple of papers have attempted to do something like this before, but they missed this. It's not super deep, but it's kind of important. What this condition basically does is a little bit cumbersome, but ultimately it's a way of guaranteeing that you have enough observations in large samples for any 1 point along the boundary. And so a condition like this will rule out, say, boundaries like these are fine, but then if you have something that does like this, well, maybe like this, right? So there is this kind of very weird kinky point there. Then it will be impossible for you to really conduct inference from this side. All the data will be on that side, but effectively there will be no data, even asymptotically in some sense, right? I mean, a precise sense, I guess. There will be not enough data for you to conduct the analysis. And so this condition is purely technical. I mean, it's obviously satisfied for simple boundaries, like the one I showed you before, this Leontief type boundary with a single kink. And it's really preventing this kind of very weird geometries on the boundary. Okay, great. So with these conditions plus the usual regularity on the underlying data generating process, then we're kind of ready to give the identification result, which is, again, not entirely, I mean, I don't think it's surprising in any way. I mean, it basically says that you can run a bivariate non-parametric regression and shrink towards the point that you care about as you construct the fits, or you can do a univariate non-parametric regression based on distance to the point. And then both of these things should agree, right? And under very minimal regularity conditions, essentially smoothness conditions on these underlying condition expectations, you will make these to work, right? So basically this object here is the important one, because this basically says that the condition expectation of Y, when you metrize relative to the distance that you decided to use, well, as you take the radius to go to 0, then remember this is a little bit of notation to just say that xi minus little x equal r. So as the radius shrinks and your ball is shrinking towards the point that you care about, then of course these condition expectations will actually agree with exactly what you think you're trying to estimate, right? And so the reason why I mentioned this is, well, first and foremost, you need a result like this to justify the methodology that people use. But more importantly is because I introduced this object, which is kind of key for what's coming next, right? So when you decided to use distance-based estimation and inference, effectively what you're trying to do is you're trying to estimate a univariate non-parametric regression locally to the point that you care about. And this univariate non-parametric regression is defined by its construction, is defined in terms of the metric, the distance to the point that you're trying to learn the value of the condition expectation. And so as you shrink the radius to that point, then of course this condition expectation eventually will agree with the bivariate condition expectation that you care about. But in the meantime, as you estimate it, you are effectively trying to estimate this one-dimensional non-parametric condition expectation that is induced from this the underlying bivariate conditional expectation through the fact that you reduced the bivariate problem to a univariate problem as metrized by distance. And here I should stop for a minute and mention that this idea is not only does not only feature in boundary discontinuity designs. Even in machine learning, you might have heard about radial kernels or some other settings where indeed multivariate or bivariate, in this case, non-parametric regressions are actually reduced to univariate non-parametric regression problems, and then inference estimation and inference is based on that. And so some of the results that we're going to present now actually would apply to those settings as well. And in fact, I'll show you, if time permits, I'll show you a particular minimax result that we were able to establish that is a little bit more general in some sense from what I'm going to say next. Okay, so let me try to explain what the problem really is and where is this coming from. And so what I do here is a little bit of an schematic analysis of how this induced univariate distance-based condition expectation comes about and what kind of features this object inherits from the underlying bivariate condition expectation that you're trying to ultimately learn about along the boundary. And so here I'm going to specialize on the treatment group only. Again, it's a non-parametric problem, so we're working on this side of the boundary. And then I'm going to consider this one point B here on the boundary. Okay, and so this point is not at the kink. Okay, it's away from the kink. Of course, this is all relative. I mean, that distance has not been yet decided, but ultimately it's not at the kink. Okay, great. And so if you're approaching the problem from a bivariate perspective, you're kind of trying to estimate the condition expectation of Y1 from the treatment group, given that Xi is equal to B. So that will be right here from the right, from inside the treatment group. Okay, and then if you were to do it based on distance, well, then basically what you would do is you will compute distance relative to the point, and then all these points that are essentially on the same arc as defined by distance. Again, for today, I guess we can think of this as just being the Euclidean distance. So it's very simple, an L2 distance. So then all these points that are equidistant in that metric, then they are all used according to the value of R that you are evaluating at. Okay, and so what I'm doing here basically is plotting on the right-hand side. I'm going to be plotting R, right, from 0 to a positive number, and on the y-axis I'm going to be plotting effectively this conditional expectation relative to the point B as a function of R. So we're going to kind of study how this univariate conditional expectation is induced from the bivariate underlying conditional expectation. And so we're going to, when you are at distance 0 or radius 0, then of course you are right here, and this point here coincides with the object that you care about. Now, if you look at a little bit of an R1 radius, right, as you move away from the point in this particular one-dimensional manifold, if you like, then what you're really parameterizing here is how this conditional expectation behaves for values between 0 and R1, relative to, of course, to the point B that you are trying to estimate. Okay, and so of course, if the underlying condition expectation, bivariate condition expectation, is smooth, then for this small perturbation up to order R1 or radius R1, the induced condition expectation happens to be smooth as well. So essentially, as you would expect, the bivariate underlying condition expectation smoothness is transferred naturally to the univariate condition expectation based on distance, according to, of course, the particular distance that you decide to use, the point that you're trying to estimate, and of course, as you will see in a minute, the features of the underlying boundary that you are facing. Okay, and so if you were to do non-parametric estimation for ranges between 0 and R1, well, the smoothness of this univariate condition expectation will help you deduce all the usual results. And in particular, if you do local polynomial regression of order P, then the bias of an estimator for the range 0 to R1 will see a function that is smooth, and therefore it will be able to exhaust or exploit that smoothness, and it will have a bias reduction of order H to P+1 in the typical non-parametric calculation. When you go to R2, nothing really changes. So you just enlarge the range that you're looking at, the function continues to be smooth, so everything looks nice, and the bias continues to be of order h to the p plus 1. When you go a little bit further, so now we go to R3, we're moving away from this point that we are interested in, and we're looking at the smoothness of the induced one-dimensional condition expectation. R3 is kind of a particularly interesting point because it's a point where the arc based on distance, this is R2, this is L2 distance, happens to be tangent or hits the kink. Okay, so this is a very special point because this is a point where the condition expectation happens to be exactly at the maximum possible distance until you hit the kink. And then if you were to increase R by epsilon more, or whatever amount that you want, as you move farther away beyond R3, something interesting happens, right? Because what happens is that now this arc can no longer be completed, right? So it would have been completed here, but all of a sudden, the condition expectation that is induced from the bivariate underlying smooth condition expectation to the one-dimensional distance-based condition expectation, all of a sudden has a change. And this change is not in levels, so the function is going to be continuous, but actually it's a change in the derivative of the function. It's the rate of accumulation of this condition expectation, if you like, that actually changes. And so we can show that a function, the one-dimensional condition expectation function based on distance to the point, when you look at the range 0 to R4, for example, this function will be no better than a Lipschitz function, right? And so this is kind of the main result that I was mentioning before. Even though you started with a bivariate, super smooth, super nice, analytic conditional expectation, the fact that you decided to use distance to the point, together with the fact that the boundary is rough, it has this kind of kink, induces a conditional expectation that whenever the arc or the range or the radius captures this lack of smoothness on the boundary, it generates a one-dimensional condition expectation that is no better than Lipschitz. And so this is kind of worrisome, right? Because what it says is that now, whenever you're trying to do non-parametrics based on distance, you're trying to estimate a function locally. Of course, locally here means between 0 and R4, say, locally that is no better than Lipschitz, which means that you cannot do better than whatever you can do for estimating a Lipschitz function. So even though you started with something that is very smooth, and potentially you could have increased the polynomial order, say, or do other debiasing techniques to exploit that extra smoothness and reduce misspecification bias or smoothing bias, the fact that now you're trying to do it based on distance, you are now you are targeting a function that looks rougher. It doesn't have enough smoothness for you to even exploit and reduce bias. And so the main result as a consequence is that distance-based functions and distance-based methods will do no better than if they had underlying condition expectations that are Lipschitz, even though they could have been much smoother than that, whenever the boundary has these kinks or other irregularities present. Of course, at this point, you could say, well, I know an easy way to fix this. The easy way to fix this is to not go to R4, do whatever estimation I need to do up to R3, right? So I will never look beyond R3, because the moment I cross R3 distance from the point, then all of a sudden I start facing this lack of smoothness induced in the underlying condition expectation. But of course, this is a pointwise argument, not a uniform argument, right? So if you view the problem from a pointwise perspective, absolutely. You can choose any one point on the boundary, arbitrarily close to a kink, and eventually, if you look at the neighborhood small enough, it would look smooth and there will be no problems. But if you actually flip the argument and you make it uniformly, you will say that no matter how large the sample size is, or how small the bandwidth is, or how local you are operating, I can always find a point sufficiently close to a kink for which your smoothness, induced smoothness, will be no better than Lipschitz. And that's exactly the result that we're going to show. We're basically going to show that no matter how smooth the underlying condition expectation is, the induced distance-based condition expectation, if you settle for the worst possible bias along the boundary, so that means uniformly along the boundary, the bias will never be better than H. Okay, that's fine, that's an upper bound, but perhaps what is more interesting is that we also have a lower bound. So you can never do better than what you would have done whenever you try to estimate a Lipschitz function. And so this is kind of the main negative result, if you like, of the paper. And of course, it justifies a little bit the simulations that I showed you before, right? So there are regions near the kinks. In this case, I show you regions near here and near there, where the bias is substantially larger, even if you increase the polynomial order. So something that is kind of interesting here is, of course, this result holds for any p. So the higher p, in this case, has nothing to add because there is no smoothness to be exhausted or used to reduce misspecification error. Interestingly, this also justifies why at the kink there was no bias, right? Because if you look at the kink point, in the kink point, the arcs vary smoothly as you move out, right? So from the perspective of the kink point, the induced condition expectation will inherit all the smoothness of the underlying bivariate condition expectation. But the moment that you move away from the kink, then there will be arcs by which immediately you will be no longer better than Lipschitz. And so that's kind of the main negative result here, which is a little bit of a downer. And of course, a natural question that you might ask is, well, is this specific to local polynomial methodology, or is there a sense in which there is no way to improve this? In other words, can we show a result that says something like, no matter which estimator you decide to use, you will never be able to do better than estimated Lipschitz functions whenever you have rough or kinks or rough behaviors on boundaries? And so for that, we have this minimax result in the
Hi,
paper.
Matias.
Yes.
Apologies for
Yes.
interrupting. There's about 5 minutes left, so just wanted to let
Perfect.
you know.
So I'm almost there. So yeah, perfect. So basically, this result here is provides an answer to that question. So what basically the result says is that if you settle to construct estimators, so no matter which estimator you decide to use, the estimator will only see the outcome variable and distance to the point. So crucially here, the estimator is not allowed to see the shape of the boundary, and it's not allowed to see the bivariate score directly either, right? So all it is allowed to see is distance to points, okay? And then you can show that no matter which estimator you decide to use, you can choose the best possible estimator in the universe that you can think of, then you will never do better than the rate of convergence for bivariate Lipschitz functions, right? So essentially the result says there is no hope to improve this as long as you decide to use estimators that only use the outcome and distance, right? So if you add more features to the class of estimators, then of course you can do better. And indeed we know that, right? Because Stone already proved back in 1982 that if you are trying to estimate bivariate conditional expectations that are sufficiently smooth, in this case, say Q smooth, then of course we can do better than n to the 1/4. And indeed, the rate of convergence is right here, is a traditional non-parametric one. And this class of estimators include this class of estimators, but also includes other estimators, in particular, bivariate non-parametric regression. And so we can definitely do better. But if you decided or have to use distance-based estimation, say because that's the only information you have available, then you will be facing this lack of smoothness whenever the boundary is rough. Okay, great. So after that, I have a few minutes, so I'll quickly summarize what else we do in the paper. So as I said before, one could stop here and say you should never use distance-based methods, but I also mentioned that in some applications, that's all you have. So you have to do something about it. And so in those settings, we try to provide some inference methods, being cognitive of the fact that you might have biases that are potentially larger than you expected. So that will change the way that you select bandwidth, that will change the way that you do inference in these settings, and we discuss all that in the paper. I mean, again, this is not a recommended approach, but if you have nothing else to go with, then maybe this is better than nothing. So you just need to be extra careful on how you do it. Okay, and then for location-based, this is pretty straightforward, so I'm going to skip it pretty much all together so I can show you some empirics before I close. But as you can imagine, all the results will go through. It's pretty straightforward. So the bias now will be of order h to the p+1, regardless of the roughness of the boundary. So they are, in a sense, these methodologies are adaptive to the roughness of the boundary. You can do bandwidth selection. You can do all the usual stuff. You can do inference as well. And all that is done in the paper. So I'm going to save you the pain. Okay. And so here is a little bit of the application that I showed you before. So in the simulations, the results were, of course, much more pronounced in terms of bias because we took 1,000 replications and we didn't really cheat it at all. I mean, we just grabbed the data, fitted it, and then we ran 1,000 simulations and we got those very pronounced biases. Here in practice, we get one realization, of course, of the real data, and the biases are not as pronounced perhaps as they were in the simulation, but they're still there. So there is something to be said about how distance-based methods behave near kinks relative to bivariate non-parametric estimation. Okay, and so with that, we also provided some inference results and some other, and all the other things, bandwidth selection and everything else for you to play with. Okay, so then probably I'll stop here, but let me just mention that, as I said before, we are now exploring a little bit the issue of aggregation along the boundary, right? So even though I still think that heterogeneity along the boundary matters and it's kind of interesting to learn about it, it is true that sometimes practitioners prefer to report a single number, some sort of average or aggregated treatment effect along the boundary. And so now we're developing some methodology based on what we have already to try to answer that question. But again, that wouldn't be super hard to do, I think. It's just a matter of aggregating and doing the dotting the I's, crossing the T's once more. Okay, so let me conclude by just saying that we studied estimation and inference methods for boundary discontinuity designs. We highlighted the existence of an irreducible, potentially large bias whenever the boundaries are non-smooth or exhibit these irregularities along the boundary, the assignment boundary. Location-based methods do not suffer from that drawback. So it's kind of a good alternative and something that we recommend. And our software package does both. So you can try the distance-based and the location-based approach. And now, hopefully tomorrow, the new version on CRAN will also have the aggregation results. And so you can actually aggregate along the boundary. Okay, great. So I think I'll stop here. So there's time for questions or comments and stuff. Thank you.
Thank you, Matias. There is one question. Maybe if it's can be answered quickly, we can do that and then move on to the discussion. So the question in the Q&A that's still open is, what will the bias be if you cheat by rounding out the kink in some way and use distance-based method?
Oh, okay. Yeah, that's a great question. So I mean, I have a couple of negative papers and people always tend to, I mean, it's natural. It's a human behavior, right? You try to fix it, right? So, okay, so let's fix it. So there are ways of fixing this. So if you remember, I said, for example, that the minimax result crucially assumed that you only had access to distance and the outcome variable, but you didn't have access information about the boundary itself. For example, in this case here, if you run, let me do it here. If you run a local polynomial regression based on distance, well, the local polynomial estimate will naturally try to fit a regression to a function that is no better than Lipschitz, right? Because it has this kind of ugly discontinuity at the kink. In fact, you can show that, I mean, the derivatives, one of the derivatives is not even bounded. So in any case, what you do then is, what you can do instead is to actually enlarge the basis function. Like, for example, you could only use the basis function up to here and then interact it and then have a different basis after R3. Right? So in other words, you wouldn't run the local polynomial regression. What is it? Here. You wouldn't run this local polynomial regression with this basis, but instead you will do an interaction for the units that are below R3 and the units that are above R3. And that is will fix the problem, of course, but now that's using additional information. Now you're using the information of where the kink is located relative to the point that you're trying to estimate. So effectively, it's using the information of the boundary, the geometry of the boundary itself. And so if you are able to do that, then you could, in principle, rely on distance-based methods. It will be kind of hard because for points that are close to the kink, part of this interactive basis now will use very little information. So it will be difficult to implement in practice. And in some sense, it will not be possible uniformly, right? There will always be regions that are sufficiently close that have no data. But I mean, of course, you could, in principle, think about that. Some other people suggested smoothing the boundary. That's something else that you can do, right? So you can try to smooth it out and then play tricks on the smoothing, maybe approaching some sort of non-smooth original bounded by smoothing it out a little bit. I have seen that as well as suggestions. So yeah, in principle, you could do that. Or you can just do the bivariate thing and be done with it.
Hey, thank you, Matias. Okay, so let's move on to the discussants. Let's do in alphabetical order. So Alberto, I'll have you share your screen first. Thank you.
Okay, let me share my screen here.
Thank you. Great, looks good.
Okay, so thank you, Matias. I'm very happy to discuss this paper. As you come to expect with these authors, you know, paper that is technically elegant, you know, and with important implications for empirical practice, like a fascinating set of questions and results. For some reason, this is not working. 1 second. It seems that this works. So, like, just to summarize the paper briefly, here we are looking at the regression discontinuity design. Like, we have like a two-dimensional running variable, and the question is like why we do this, and the answer is that this is a very, very natural setting in many practical applications. Like Matias mentioned some of these, like the treated units may satisfy perhaps like two requirements, like merit and need, or at least one of two requirements. Perhaps you need to have sufficient merit or sufficient need. In another application, type of applications that Matias also explained, like exposure to treatment may depend on the jurisdiction where the unit is located. Different jurisdictions like have the different policies, like perhaps you know, you can think that, you know, people who live in different jurisdictions but live close to each other, live close to the boundary, are going to be like quite similar, except for some of them are, you know, affected by one particular policy and the others not. And something that you don't see that often, but is also true, is that in some cases, like even if you have one-dimensional regression discontinuity design, you may want to try to explore like heterogeneity treatment effects, but by adding an additional dimension. You may think like, I'm going to add some covariate to this problem. I will have a two-dimensional boundary, and I will see how, you know, like the effect of the treatment is going to vary across this boundary that you know represents some variable that I care about. Okay. Just to make things like a visual, this is the idea of the regression discontinuity design. Like in the first plot, you have the treatment assignment. Perhaps to the right, you know, like the units are assigned to a treatment. To the left of the boundary, units are not assigned to the treatment. And you can see the regression function in the second plot. And here what you say is like two things. Like we have like you know, the two regression functions. We are going to assume that they are sufficiently smooth. But, you know, even in that case, you know, of course, like you're going to have like different treatment effects for different like points, you know, along the boundary. And that's going to make the estimation problem like, you know, like more complicated in some way, but also the results are going to be richer. Okay. So I'm going to talk about the blessing of the boundary and the course of the boundary. Like one of the blessings of the boundaries that in empirical practice, in fact, like we see this type of settings in which the treatment assignment is often a deterministic function of the observed features. And one is one example is the example of the Columbia, you know, if I remember, college scholarship program that Matias was talking about. Another reason why, you know, like a bidimensional boundary may be interesting is because, like in regression discontinuity design, we care a lot about a potential, you know, manipulation. Like people may decide to locate themselves in one or the other side of the boundary in order to, you know, get treatment or to avoid treatment. And when the assignment really is more complex and, you know, the boundary has like two components, it may be difficult for people to, you know, manipulate them. in a way that they are going to, get access or avoid the treatment. Okay, and also what happens in some cases is like the boundary is going to cut the population in more than one dimension, as we saw in the application that Matias was talking about. We are going to obtain a richer description of the treatment effect. If I remember correctly, in the application, it seems to some extent that the effect of the treatment is going to be smaller for for students that have better academic performance. So that's something that we may be interested about. Okay, so what are the course of the boundary? Like Matias explained it very well. Treatment heterogeneity always makes estimation harder. Like we can think about first, what are the estimates that we care about? We'll have to, aggregate this treatment effect in some way, because we have many, one for each point. Matias was talking about post-aggregation, so you're going to estimate the treatment effect for each of the, points in the boundary, and then you're going to aggregate it in some way that makes sense to you. I think that this is the way to go. As he also mentioned at some point, many people, I think today many people are like pre-aggregating, so they are thinking about, we are going to take this empirical application in which I have like a two-dimensional boundary, and I'm only going to think about comparing the people that are close to the boundary and on one side of the boundary, and the people who are close to the boundary and the other side of the boundary, without regards of where exactly on the boundary they are located. So this is a practice that you see often there. You can call it pre-aggregation, and it will be interesting also to think about what happens in that case, and in which cases this could be a good practice, and in which cases this shouldn't be done. Another problem with having a two-dimensional boundaries that you will have sparse data. This is the course of dimensionality, and also something that we may not like is that suddenly the geometric properties of the boundary are going to become very, very relevant. In Matias, here we have three plots. Matias was talking mostly about the situation that we have in the first plotting. We have some kink in the boundary. Of course, you had I think he mentioned it again. You have you may have settings in which you have a kink, and close to the kink basically you don't have data, and that's may make estimation difficult even if you are looking at the location model. And then you can have settings like the third plot, in which things look nice and smooth, and you think that you may not have problems, but also close to the boundary of the distribution of the running variables, you are going to have kinks that are created by this boundary, the second boundary, unless you have some type of smooth passing, and that's also going to create problems even in the boundary looks really smooth. Okay, another problem that you could have in terms of regression discontinuity design when you have two dimensions is that the continuity of the regression functions at the boundary needs to hold in both dimensions. And this may be a problem in some applications. For example, in the application of the Colombian program, perhaps one of the variables is used to assign this scholarship, but it's also used to some other anti-poverty program, active labor market program, and so on. So the more dimensions that you have, the more things that you have to check in terms of, do I have, do I expect to have continuous regression functions in both dimensions? And finally, something that sometimes worries me in terms of the spatial or geographic regression discontinuity design is that we are comparing people around, in two sides of the, a boundary of two jurisdictions. But of course, this jurisdiction may have different policies in one particular policy issue, but may also have very other very difficult different regulations, different types of school, maybe different in many other respects, and that's something that one has to be aware of. The univariate distance approach is very simple. Just reduce the problem to one dimension, assign distance to the boundary, I will not go over this again, like Matias explained it very good. Like this is going to create uniformly, it's going to create a bias of order h, in terms of a polynomial, local polynomial regression, like irrespective of the order of the polynomial. And you are going to have also like a bivariate course of dimensionality. It means like not by reducing in one dimension, like you are going to have the result that you would expect to have, like in the one-dimensional regression discontinuity design. And to some extent, these are great observations, by the way, but to some extent, it shouldn't expose, at least it shouldn't, surprise us, because otherwise we basically would have found a way to beat the course of dimensionality, and we know that this is quite difficult. However, if you approach this point B along any of these rays, I think that is the intuition. If you approach it like in terms of distance, you're going to have this type of non-smooth functions. But you approach this point B along any of these rays, you're going to have a nice a smooth regression, and that's why the location model is going to work. Okay, I mentioned before I did a very fast simulation, using the software that the authors are have posted on the web. And this is something that I found, or I should say, a very good array of mine found in the a bivariate regression discontinuity design. This is a very, very smooth linear boundary, but still because of the problems that you have of kinks that appear at the boundary of the distribution of the random variables, you are going to have bias. So at some point we're talking about perhaps you can use distance if the boundary is smooth enough, but it's not clear to me, and in which cases the boundary will be smooth, given that even in this case you may have some problems. The bivariate distance is going to solve all these problems. It's going to be robust to boundary kinks. But as we said before, if the boundary is very wiggly, you may have we may have still problems in terms of inference. Remember this a boundary that we have that was like a curly V, right? And I took this picture from a paper from one of the co-authors from Rocío, a different paper, and you look at this spatial regression discontinuity design, and something that would be very, very useful for me is to have an answer to the question: is this wiggly enough or is not wiggly enough? What should I do in this type of settings? How can I, as empirical researcher, judge whether even the bivariate distance is going to be something safe for me to apply in this context. So yeah, so that's all what I have to say. Again, a great paper, I think is going to be widely used, very useful for empirical researchers, and yeah, thank you very much. That's it.
Thanks, Alberto. So we'll move straight to Kosuke. Kosuke, please feel free to start whenever.
Okay.
Thank you so much.
That's this. Okay.
Looks good.
Yeah, thanks for inviting me as a discussant. It was a pleasure to read. I'll just go quickly. I know the time is pressing. So I think this boundary RDD is, we see this all the time. I think most important applications are geographical boundaries of administrative units. And so I think, this paper is going to have a big impact on the practice. And I think, heterogeneity of the treatment effects estimation, that's pretty hard thing to do. Matias made it sound like it's easy, but it seems pretty hard. The paper had a lot of technical rigor, and the thing it impressed me most is sort of uniform inference. That's going to be quite useful as people explore the treatment effect heterogeneity along the boundary. Okay, and then there's the awesome software. So this discussion is a little bit fair to some extent, because I learned everything about RDD from Matias and Rocío. So to discuss their paper, it's a little bit difficult for me. But I had a couple sort of questions that are what the author was trying to do, I think, as a next step. So maybe this will be useful for what they're going to do next. Okay, so, okay. So the first question, I think Matias had a little bit of time at the end to talk about how to compute the average streaming effect. So this is sort of not just the streaming effect, average streaming effect at each point on the boundary, but averaging over all the points on the boundary. So I think that seems like first order things that the practitioner would want, before they go to this method where that gives you heterogeneous streaming effects. So I think the suggestion at the end was maybe we can just sort of average over this heterogeneous streaming effects using the density over the points on the boundary. Okay, so this seems reasonable, but it seems also a little bit hard because you have to, I guess, basically do a density estimation around the boundary. Maybe difficult, some parts are quite sparse and so on. So that's sort of the one potential approach. And I was thinking maybe there's maybe an easier way. And so here I'm thinking about univariate distance based. So the approach that probably is not a good idea for the heterogeneous streaming effects, but I'm wondering if we can do this for the average streaming effects. So here you basically have the sign distance function where you compute, say, Euclidean distance to the nearest boundary point from every point you have. And if you're on one side, you have a positive distance, and if you're on the other side, you're on the negative distance. So my horrible hand-drawn picture is like this. So if this B is the boundary, the red line, then the treated group is on the right above corner, and you can see the equal distance point has the same exact shape as the boundary, and then same thing with the other side. What's nice about this is that if you have like a kind of crazy looking boundary, now my handwriting is like completely breaking down, but you see that the equal distance point sort of keeps the same shape of the boundary, and you can extend this in all sorts of ways. So I find this to be nice because it sort of groups all the points that have the same distance from the beginning. So there's no point of, you don't need to average over the density on the boundary points. It's basically everything is grouped already based on the distance to the nearest point on the boundary. So and so it's basically the boundary only has to be piecewise smooth, and this function will be differentiable. So it sort of keeps the smoothness even in the presence of kinks and other maybe irregularities. So if you can maybe approximate even the crazy ones with a piecewise smooth function. And there's actually, this is not something I know anything about, but there's a fast numerical algorithm to compute this, because this could be quite hard to compute if the boundary is very wiggly. But it sounds like people have developed in using data, you can compute this very quickly. And so maybe then like we can just use local polynomial regression for this sign distance function to estimate the average streaming effect. I haven't verified this claim, but if that's actually the case, then I think it's a nice sort of easy way for the practitioners to look at the average streaming effect before they explore the heterogeneous streaming effect estimation. The last three, I was thinking a little bit about the spatial RDD, because I think that's sort of probably the most frequent application of this method. Alberto already mentioned the treatment bundle issue, so there's really no solution to that. I was also thinking about interference between units, but it turns out I don't think it's really a problem, because I guess all you're thinking about is the counterfactual of everyone on the boundary is being treated versus nobody else on the boundary is being treated. So that two counterfactuals holding everything else constant, still well defined. So that's nice. So the last question, I guess, is the spatial dependency. So here, I think we've been assuming this IID observations. I think in Matias' application, it's pretty reasonable. But a lot of spatial RDD setting, there may be a spatial dependency which may affect uncertainty quantifications. So that's something that I'd be interested in knowing how to handle that. Thank you.
Excellent. So Matias, back to you. We have about 5 minutes to answer all of these questions. So good luck.
Oh, okay. Wow, that is okay. I let me just say that thank you so much for the comments. I think they were both, I mean, right on spot, and this is kind of another to-do/wish list. Let me briefly mention that. I mean, let me go in order, I guess. So Alberto asked the question, what too wiggly is, and of course, as most uniform type results, I mean, we don't really know how to quantify what really wiggly means. That's a hard question. I agree that that example that you pull out and many others that are geographic based, they tend to have boundaries that are quite rough, right? So underlying these notions, if you look at the appendix, we need to somehow parameterize this one-dimensional manifold, which is a boundary. And ideally, we parameterize it by some smooth curve, right? And so this smooth curve captures, at least mathematically, how the smoothness of the boundary and allow us to make progress mathematically. But in practice, I mean, is it smooth enough, or do we have enough roughness or kinks or irregularities that we have to worry about? I think it's a great question. I don't really have an answer. I don't think neither of us do at the moment. So it's something that definitely is on our wish list to try to understand or disentangle hard boundaries from easy boundaries if you care about heterogeneity along the boundary. But then for Kosuke's point, I completely agree. So I basically rushed through this partially because we are working on it right now. So I wouldn't have all the answers that I wish to have at the moment. But I mean, let me just mention here the slide in a little bit more detail. I think what Kosuke was ultimately asking for is the connection between what we call the pool OLS analysis, which is exactly this idea of constructing a band along the boundary and then just running a difference in means or a local linear regression interacted with treatment assignment variable, right? A local polynomial, if you wish, along the boundary, along the band, pulling all the information together. And this is something that people do. I mean, Alberto pointed this out before. I think many people do. People also throw in fixed effects, which to me is also kind of still up in the air of why people would put fixed effects for location or something like that. But if you look at some of these papers, often people do. And so it's perfectly fair to ask the question how these things connect. Our initial back of the envelope calculation suggests that indeed those least squares pool-based methods on the band would ultimately be estimating some parameter that could be represented as the parameter here for very specific weights, right? And the weights will be either some conditional density, right, or density, as Kosuke suggested. He was using the marginal density along the boundary as weights and things like that. So this is something that we are currently investigating. And another thing that is also interesting and perhaps, again, not unsurprising ex post, Alberto mentioned correctly, of course, that ultimately, even if you reduce to one-dimensional distance-based non-parametrics, your rate of convergence has to be that of a bivariate non-parametric problem, because otherwise you would be breaking the curse of dimensionality. And so in the language of local polynomials, the rate of convergence is of order 1 over n h squared. The two coming from 2 dimensions in this case. But if you were to do Kosuke's idea of running this kind of aggregation or pooled along the boundary, then you're really estimating a non-parametric function in a one-dimensional manifold, which is a assignment boundary. And so it's not surprising and perhaps to think that perhaps the rate of convergence will no longer be one of the bivariate non-parametric estimate, but by virtue of the aggregation, you can actually do better. And the rate of convergence would be likely something along the line of 1 over n h. H here will be kind of the width of this band, right? So you're kind of doing non-parametrics in a one-dimensional sense because the band is shrinking to approximate the assignment boundary. So again, these are all questions at the moment. I mean, some of these we have verified by back-of-the-envelope calculations, and we're hoping to write a follow-up paper that kind of answers all these more precisely. But yeah, again, thank you so much for everything. Let me just mention that Kosuke talked about sampling beyond IID. In our software, we allow for clustering as a way of mitigating this spatial autocorrelation to some extent, but our theory nonetheless does assume independence along observation. So again, it will be an interesting theoretical exercise to work through the more complex sampling designs that you typically see in geographic settings. Okay, I'll stop here. Thank you so much.
Wonderful. Thank you, Matias. And so then I will share the screen to end. Okay, great. So just before we sign off, I'd like to thank Matias again for a wonderful talk, and Alberto and Kosuke for also great discussions and asking a lot of questions, and also for staying all the way until the end. Next week, we'll have a talk by Julie Jost from pre-medical INSERM team at the University of Montpellier on causal alternatives to meta-analysis, and our discussant will be Larry Hahn from Northeastern. So I hope you all join us for that. I believe that will be our last seminar for this academic year. So thank you all again, and have a great rest of your week.